To kick things off, our keynote speaker is Dr. Chris Cooper, Emeritus Professor of Biochemistry from the University of Essex. He's authored hundreds of journal articles. Many of these are related to near-infrared spectroscopy. He's presented at many conferences, and he's written a couple of books, including Blood, A Very Short Introduction, and Run, Swim, Throw, Cheat, the science behind drugs in sport, which is also can somewhat be related to, there's some overlap with near-infrared spectroscopy there as well. His topic for today is models for the interpretation of muscle oxygen data. So this will be about a 50 to 55 minute presentation, and we'll have about a 5 to 10 minutes for questions and answers at the end. So thank you very much, Dr. Cooper, and I'll turn the presentation over to you.
Okay, thank you. Well, it's just a great honor to be the opening speaker in this, probably my first virtual meeting. I know you do webinars all the time. This is my first virtual meeting, and I should, if I was clever, I'd have had a backdrop of Prague behind my face, but I think you've got, if you're looking, oh gosh, I've got Niagara Falls behind me, so I'm not in Prague. I'm also not in Niagara Falls. So I'm giving this presentation about interpreting muscle oxygenation data. As I said, it's a great honor to be the first person to present at this meeting. I'm going to give a general sort of overview of the technology as I see it from my history of working at muscle oxygenation, and then go into some specifics of work around sport and exercise science, in particular training studies. So I'm going to apologize to two groups of people because it's quite technical, this talk, but I'm trying to explain it hopefully in a very simple way. If I'm too simple, and you've heard it all before, the beauty of a virtual talk is you can just go to sleep or twiddle your thumbs or do something else, and I won't know. So that's completely brilliant, the way of doing this talk. If it's too detailed or too complicated, I'm available to answer questions on the Discord space afterwards or ask a question. No question is too idiotic. And in fact, sometimes the idiotic questions give you insight as a speaker when you think of new things, because especially if you're practical and coaches. So with those caveats, I'll head on with the presentation. I will do if it will. Yes. So the outline of the talk, I'm going to talk about what near-infrared spectroscopy measures, how does it measure, similarity and differences between machines in particular. If you want to stop the questions halfway through, I see what Roger wants, we can break then, and then I'll move on to the second half of the talk, which is probably more like the final third of the talk, with some practical uses of the spectroscopy, some more quantitative physiology, and then some new analysis ideas that I've got, and which I hope you will be able to bring in the course of the meeting. So, what does this technique measure? Well, what near-infrared spectroscopy does is it reports indirectly on oxygen delivery and oxygen consumption. So obviously we pick up oxygen in the lungs, transported in the blood, and consumed in the mitochondria. And by measuring parameters of the blood oxygenation and blood volume, we get indirect measurements on probably things you want to know about, which is oxygen delivery and oxygen consumption.
Hey, Chris, could you start the slideshow presentation?
Oh.
So that we'll be able to see your slides a little better because right now we're seeing like your presentation is in edit mode.
Start the slideshow. So stop. So hold on. So in the webinar, I say start.
No, this would be in the PowerPoint. In the PowerPoint software, go to slideshow, start presentation.
Okay, hold on. I thought so in the slideshow it says.
So just like you were going to present live.
Yeah, that's what I was doing actually. So I do this. Do you not see it?
Nope, we still see the edit side. You might need to switch if you have two monitors. You might need to move it back to your main monitor.
I've got one monitor. Have I got stop sharing screen there? Does that help? No. Is that any better? No.
Nope. So go to share your screen again. There might be a glitch in the driver.
Stop sharing my webcam. That help? Hide my webcam help? Was that not me?
Go back to sharing your screen. Just
go back to the PowerPoint.
Yep.
So this is not helping you. I still having the problem. You're only seeing a small part of the image. Is that right?
We're not seeing your screen at all right now.
Hold on. Not seeing my screen?
Nope. Let me see.
No. Hold on.
Still the presenter.
Change, no, don't want to change presenter.
In the webinar software, there should be a show your screen icon.
Hold on. Stop. Questions chat. Webinar control panel. It's got paused here, so if I pause it somehow, but if stop, I've got to stop sharing screen, but it's not. Yeah. When I keep pressing it, it keeps saying pause.
Show there you go. There you go. Now it's working. Now it's working. We're seeing your hemoglobin protein carries
click away.
There you go. Now hemoglobin
you okay
colors.
now still?
Yep. Now it's working. Okay. That's what we want. That's what we want. Go ahead.
So, right. So, okay, brilliant. So, as you all know, most of the oxygen in the blood is carried in red blood cells on hemoglobin, and hemoglobin has lots of different wonderful colors, depending on the form of it. But the key forms that matter mostly in biology and certainly in spectroscopy are the oxy form of hemoglobin, which is bright red, and the deoxy form, which is kind of a claret. And this shows you the structure of hemoglobin as it changes oxy and deoxy, and it changes its color. And on the right-hand side of the slide, as I'm looking at it, you can see the pure hemoglobin protein and the different colors in the visible light. So I've not got my mouse. I was going to use my mouse, but that's not working to show you the screens. That's fine. So I'll just describe it as I'm going along. And that's the pure protein I showed you here. But if you look here, this is the oxygenated, deoxygenated blood in a blood circulation circuit, showing the difference in colors there. And those are visible light colors, but we're looking at near infrared light, so between the 700 and 900 nanometer. And we use that light because visible light, as you can see from the top slide, absorbs very, very strongly. Hemoglobin absorbs very strongly. And near infrared light on the longer than 1,000 nanometers wavelengths absorbs very strongly by water. But between those two wavelengths, you get smaller absorbance, and therefore light can pass through tissue. So if you shine a torch through your skin or your surface, you can see red light coming through, easy to do with your fingernail. And actually near infrared light will go even deeper into tissue, all the way into the brain, all the way into muscle. But it has to interact with tissue as it goes through. And it does interact, and the light can be absorbed. So there's, as well as visible colors, there are near infrared colors for oxy and deoxy hemoglobin, and they're different. So you can then tell them apart in principle. There's also another protein called cytochrome oxidase inside the mitochondria. It has a very strong near infrared signal. I spent about 30 years on that, and my PhD was working on that protein. It's very difficult to detect. So, and certainly in the muscle, it's even harder to detect than in the brain. So I'm not going to talk about that anymore. There's also another protein that I'm not going to talk about much, but I'm happy to discuss later after the presentation. That's myoglobin. So inside the muscle cell, we have a protein that's involved in intracellular oxygen transport that looks exactly the same color near infrared white light as, so absorbs the same near infrared light as hemoglobin, and therefore you can't tell it apart. And it's anywhere up to 30 or 40%, maybe 50, maybe as low as 10. No one quite knows. But certainly when we talk about hemoglobin, we're really talking in the muscle about hemoglobin and myoglobin. Hemoglobin in the blood cells and myoglobin inside the muscle cells. I won't talk about that anymore. Just assume I'm talking about myoglobin as well as hemoglobin in most of the talk. So to understand how near infrared spectroscopy works, it's useful to discuss a related technique called pulse oximetry. Very important technique at the moment. Pulse oximetry measures the arterial hemoglobin saturation. So that's the ratio of oxy to total hemoglobin in the arteries, which tells you how well your lungs are oxygenating blood. So you can be absolutely sure every COVID-19 patient in hospital is having one of these devices measured on them all the time to make sure their lungs are working, and their care will be determined in large part by the numbers on this device. But remember, it just measures the arterial blood. In fact, it locks into the pulse of light. Therefore, you need to have it somewhere where you can detect the pulse of light, for example, on the end of a finger, and it measures just the arterial hemoglobin, which is great if that's all you want to measure. But if we want to measure in the brain or in the muscle and see what's going on with those tissues, we need to get information from the capillaries or the vein. And this shows you my student measuring on the vastus lateralis of a synchronized swimmer, a Russian synchronized swimmer, with a device. And in that muscle, it's measuring a mixture of arterial, capillary, and venous, probably about a third, but exactly what measuring is not clear, and it will probably depend on a whole range of factors. So, but broadly speaking, it measures a mixture of those three components. Now, how do you measure color changes? How do you convert a color change? And by this, I mean an optical density change, how much light is absorbed on the y-axis of this graph. How do you measure that with near-infrared spectroscopy? Well, you take advantage of the fact that different wavelengths absorb light differently for oxy and deoxyhemoglobin. So if I'm measuring, if I've got a conversion, of oxy to deoxy, if that happens at this wavelength here, you'll see an increase in absorbance, for example, 760. At this wavelength here, like say 870, you'll see a drop in absorbance. And if you measured here, that's what's called the isosthetic point, you see no change. If you measured oxy plus deoxy, if there was a change in both oxy and deoxyhemoglobin at the isosthetic point, you now see an increase because they're both contributing to the absorbance change. And so essentially, as a bare minimum in any near-infrared spectroscopy device, and actually this works for pulse oximeters as well, you've got two unknowns, oxy and deoxy. You need at least two wavelengths to make a measurement. And you can use more wavelengths for a whole range of other reasons, but the minimum is two. And if you look, this is from a review in 2016 by Bruno Grassi and Valentina Quaresima. And if you look at the number of devices used for measuring muscle in that time, the light sources, they either use LED or laser lights, and anywhere from 2 to 5 wavelengths are used. If we narrow down to devices probably of more interest to you people, ones that are portable or wearable, again, they use 2 to 3, 4 wavelengths. The Moxie uses 4. The portable one I'll talk about uses 2. So I'm going to be largely at this talk talking about the Moxie and about the Portamon device. There are other devices available. I think the BSX Insight, well, they've gone bust now, so that's no good. There's Japanese, Italian, I think potentially there's a slightly virtual company in Canada also measuring devices. These companies come and go, but obviously the Moxie carries on forever, we hope. So what does near-infrared measure? How does it measure it? And what are the similarities or differences between machines? Why are there so many machines? How do they work? And are they different in any meaningful way? First question you always get asked, when we started measuring in the skull, saying we're measuring in the brain. When you put it on your leg, how you know you're measuring in the muscle? Where does the light go? I'm taking an image here courtesy of Roger's previous company, Hutchinson Technology, showing the source and the detector and the light going through the tissue. The easiest way to remember where the light goes, and this is basically using light transport models, is to say it's just got the shape of a banana. And that's an easy way of knowing where the light goes approximately. This is perhaps a more sophisticated hallucination of where the light goes. And what you see here is as the light transfers to the tissue, it changes its color as it goes from the arteries to the veins. And you can pick up the mixture of what the color of light is. The further apart the source and the detector are, the deeper the light penetrates. So this is showing that when you get to 4 centimeters of you can probably get 2 centimeters depth of light penetration. And a rule of thumb is that depth of penetration is half your source detector separation. So if you've got a source and a detector at 4 centimeters, you get 2 centimeters penetration. There are tricks to get around that, and I'm really looking forward to Roger's talk where he'll show how you can get depth penetration that's a bit better than that by using various fancy tools and methods. So, but in principle, that's what you get more penetration the further the source detector is. And if you're measuring at different source detector separation, you will see different parts of the tissue. That's one of the features. If you're imaging, that would be a big feature. If you're not imaging, you need to take allowance of where you're actually measuring. So how do we measure a concentration with light? We've now got light being absorbed by the tissue. And the basis for this is what's called the Beer-Lambert law. If you look at the top part of the slide, the amount of light absorbed, or the OD, equals a value dependent on what the protein is, which bit of hemoglobin, whether it's oxy or deoxy, its concentration, how much is there, and the path length. So it's really simple to solve, if you know those numbers, for the concentration of your protein. But if you look at the second half, the bottom of the slide, it's much more complicated because in a scattering medium, the light bounces around and you don't quite know what the path length is. Some of the light doesn't get to the detector. So you need to apply some sort of correction to allow for the fact that it's not a simple, nice test tube. It's a lump of tissue. That's hard. And how you do that is done differently in different machines. But the basic core measurement that every near-infrared spectroscopy device can measure, even though they don't always give you the output, is to use a different spectroscopy. So you just assume that there's no scattering change in your measurement. So you always have to blank your measurement at the start and say, what's the change? What is the color change in the measurement? And you assume there's no scattering change, and therefore you're just measuring the color change. And if you do that, you can measure a change value for the change in deoxyhemoglobin, a change in oxyhemoglobin, a change in total hemoglobin, and a change in oxygenation. And they can be in micromolar units, or and that gives you an actual concentration change. Every device can give you that number, but actually people want to have not a change number, they want to have an absolute number. They want the machine to go on and give them a number there and then. They don't want to do this to change in the assumptions. So that's the simplest thing. And some of the measurements I'll discuss later on use these raw numbers, these change numbers. But other devices want to measure, so other machines want to measure absolute numbers. So to have in effect the pulse oximeter giving you a saturation, but a saturation in the muscle, not the arterial blood that's the same all around the body, but a saturation in the muscle. So the fraction of oxy over total hemoglobin, and you multiply it by 100, you get a percent saturation. So how do you correct for the scattering to get these absolute numbers, not just the changes? And there's a range of ways of doing that. If you've got a very expensive machine, 30, 40,000, 100,000 pounds, you can do that. In portable near-infrared spectroscopy, there's really only two methods that have been used, or two types of methods that are used. Unfortunately, they've both got almost similar acronyms. One is what's called spatially resolved spectroscopy, or SRS, and that's used in the Artemis Portamon at the moment. Another is, there isn't really a set name, but I've called it spatial resolution spectroscopy, and that's essentially what the MOXIE uses. And they differ by where they put their light sources and their detectors. And that affects how the measurement works. I'll describe that now. First of all, starting with the Artemis and then moving on to the MOXIE type measurements. So the Artemis device takes advantage of the fact that light, when it's scattered beyond a certain distance, is homogeneous. So the scattering is the same however far apart you are. It's a constant component. And you can see that best in the image on the left-hand side of this slide as I'm looking at it, where you see, this is just a flash from a smartphone, and that is a bottle of probably dilute milk, it's a scattering material. And you can see that the white light goes in, and you don't get a single beam coming out. You get an equal distribution of the light from wherever it comes out at all sides. So the scattering, therefore, is the same no matter what the source detector separation is, wherever you're measuring. So therefore, if you have a light source and three detectors very close together, for example, 3, 3.5, and 4 centimeters together, the change in absorbance, if you look at the left-hand side of the slide, the delta A, the change in absorbance between the 3, 3.5, and 4, there is no difference in scattering. So the change in light reaching the detector between those three distances is solely due to absorbance. And then you can use that to give you the absolute number for hemoglobin saturation. So that device So every device that has that kind of setup, where you have a source or a detector and then a distance away, 3 sources or 3 detectors very close together, uses the same technology, originally designed using the Hamamatsu device and the Portamon device uses it now. They broadly measure by the same way. Now that's not true for the next technique, which the MOXIE falls into, and that's what I called spatial resolution spectroscopy. And that takes advantage of the fact that there is, in the places we want to measure, like in the head or in the muscle or in the arm or the leg, there's always a superficial layer, and there's nearly always a region of interest that's deeper. So in the brain, we'd be looking at the superficial layer being the skull, and in the muscle, the superficial layer would be the skin and the fat layer particularly. And so what you do then is you take one source and then a detector that's halfway between a more distant detector. So the MOXIE, you've got a 1.25 at a 2.5 centimeter detection. And broadly speaking, by fancy tools and algorithms, you essentially cancel out the superficial layer or subtract it out. And you can see a simple subtraction will be, well, one minus the other, but you do a bit more than that. And that gives you the number solely from the deeper layer and allows you to measure an absolute saturation. The problem with that technique, it's not really a problem, it could be a feature, is that there's all sorts of different ways of making that measurement. The whole range of different algorithms are used. And so if there's an SRS device, I know they'll all be the same, or at least they should be the same. But the devices that have a source and a detector and another source halfway distance, so as I said, A1 and A2 device like the MOXIE, may not be the same as another device. Here's an example of a few devices. I think on the left-hand side are some companies that have really made, probably the few companies that have really made any money with proper money with near-infrared spectroscopy. These are devices used in clinical critical care, predominantly to measure infants' brain saturation. And they use a subtraction approach like the MOXIE, but a fundamentally different approach to the MOXIE. But they still use that same device. So you need to be aware that you can't always compare numbers. Even though they're saying they're giving you a saturation number, they may not be the same with different devices. And that's problematic if you're an academic. It may not be problematic if you're a coach and you're just always using the same device. But you need to be aware of it when other people are talking about these kinds of measurements. So I thought I'd give an illustration of this by comparing some recent work we did comparing the Portamon device, an SRS one, with the MOXIE SR, a paper we published a couple of years ago. And the first slide really illustrates a feature that I could say in like 20 or 30 papers of this type. You take two devices that claim to measure a saturation in muscle, or usually they're in brain, and they correlate, but they're not the same. And this shows you two 30% and a 50% maximal voluntary contraction in the arm using the Portamon and the MOXIE. And in both cases, you can see the 50% gives you a deeper drop in muscle saturation, but they're not the same. So they will correlate if you compare one or the other, but the absolute number will be different. And then the question is, they correlate, but which one is right? And that's been an issue around the field for 20, 30, 40 years. And what is right? Because actually, the MOXIE is measuring a different tissue than the Portamon anyway, because the Portamon probably measuring a deeper, because it's got a bigger source detector separation, a different value anyway. And then we don't know whether it's arterial, venous, or capillary. So there's lots of issues around understanding what the measurement is. Doesn't mean it's not useful. And that's why I'm really excited to see what use you make of it, because it's still measuring something important in the tissue. So don't ever forget that. It's just exactly what that number means different things to different people. But don't worry about it. You know, if it's useful, you should be using it. So to illustrate the distinction between the Portamon and the MOXIE, one thing I noticed was that with males, we saw at rest, measuring on the vastus, on the thigh, we saw no difference. And the resting number was the same. But with females, the MOXIE was giving us consistently and significantly a higher reading. Why that could be, we don't know, but whenever I see a male-female difference in optics, and I usually think of surface fat layers, because if you have relatively fit males and relatively fit females, there's a big difference in the surface fat layers. Even in athletes, there's quite a big difference. And females have larger surface fat, and therefore it's usually the first place I would look at to see is there a distinction between males and females. And indeed, if you compare the MOXIE and Portamon, when there's not very much surface fat, as you can see from the left-hand side of this graph, the devices are pretty much the same. They're not different. And as you increase the fat content, these are still not by no stretch of the imagination of these obese individuals, or even not, fit and healthy individuals. But you see a distinction. Both the devices do change as you change fat levels, but they're differently. They change differently. Possibly their contribution to trend corrections are different. Doesn't mean we know which one is right and which one is wrong, because it's possible, for example, that females have a different resting saturation, and therefore, by accident, you'll see a difference in the fat lengths. We don't know the answer to that question. How do you correct for these issues? And I'm going to show two ways of correcting for it. One, and they'll illustrate different points about near-infrared spectroscopy devices and the way you might want to use them. First is a machine does the correction for you. And I'm really interested in seeing Roger's talk later on, because that's what the MOXIE does, essentially. It provides, within its machine, its algorithm corrects for the fat. That's what it tries to do. This is a device that was marketed about 10 years ago now, Japanese device, and it did have a fat correction, but interestingly, the user themselves made a measurement. They made a skin fold measurement, and they fed that into the device. So I think that's a good idea, actually. And certainly, if I'm reviewing scientific papers with near-infrared spectroscopy, I'm always telling people I need to know what the fat layers are, even if you're just using a caliper, nothing more sophisticated. I need to know what they are, because that has an effect on interpretation of what's going on. So measuring it and correcting it's quite interesting. And we're all in COVID-19 time modeling experts now, and we all know models are only as good as the data you put into them. So I think this is a good idea, actually. It didn't catch on that company's no longer making near-infrared devices, but I think it's an interesting idea. And it does matter. So this is not the MOXIE. This is data I did using, it was using a Portamon, but actually it wasn't using the Portamon algorithm at all. It was just using it to make the measurements. And I was comparing male and female biathletes. So these were fit individuals. They were doing treadmill running at different intensities, and you can see as they went to higher intensities on the right-hand side of the graph with longer time, they were desaturated. But there's quite a big difference between the males in black and the females in green. But once you apply the fat correction, which I did by a modeling tool, had made the measurements and applied a correction, that difference got much smaller. So in fact, the males got less saturated, the females got more saturated. So that shows you the extent of the changes that can matter if you do fat corrections, or you get fat corrections wrong, and I'm sure the MOXIE doesn't get them wrong. But if you get it wrong, it makes quite a big difference. So it's an important point to bear in mind when you're making measurements. Certainly, if you're making measurements on individuals that are not fit, and have quite variable fat levels, you can get big differences. So be aware of that. One thing I should say is that although the fat correction might make a difference to the absolute number, it's still not affecting the overall trend. So if you look at each individual, you're getting, as they decrease, as they do more work intensity, they're dropping the saturation. So it affects the absolute number, but doesn't necessarily affect the overall trend. Again, that's useful to know. There's a second way of doing these corrections, and that's not sort of machine algorithm independent, and that's something the user can do. And I'm going to talk about this particular method, not just about correcting for differences in fat layers, but also for reducing variabilities in your measurements. So this method might be also, as well as a way of, and it's been shown to have an effect on decreasing the variability due to different fat layers, but also potentially might decrease variability if you're making a measurement on different individuals, or one individual at different times. And that's what's called a physiological calibration. And I didn't used to be a fan of these for a range of reasons, which I can talk about offline or online later. And that is an intention to standardize a test between and within subjects by making the subject his own 0 and 100%, not the machine. So obviously the machine will give you a number, But what you then do is you do an ischemic calibration, so an arterial occlusion, and that drops the saturation, and you say, well, that's the zero. At that point, all the oxygen's been consumed, there's no blood going in, it should be zero. Then you release the cuff, and the blood pours back in, you get an increase in blood flow because there's a hyperemic effect, and that's 100% oxygenated. Now, I have doubts whether the first one is really zero and the second one is really 100, but you use those numbers to calibrate the individual's device measurements. So it gives you an extra way of comparing between individuals if you're not sure that they're really comparable. And I'm more of a fan of that since I did this paper with the comparing the portable and the Moxie, because as I say, they give different numbers, and I'm not saying which one is the right absolute number at all. The Moxie does seem to give a deeper saturation drop. So it gives you a bigger dynamic range, actually, which is quite nice. So this shows you a typical trace with a patient, not patient, a runner, and as they increased exercise intensity, both numbers fell, but they were different. But when we did a calibration, now the difference between the two devices went away. So within their own internal parameters, they were measuring the same things. That's quite an interesting phenomenon, which gives me some hope that if you're not sure about something, or you've got a slight confusion in the measurement, doing that kind of calibration could be helpful, might tell you what's going on. So that's kind of my Mickey Mouse introduction to near-infrared spectroscopy. And I've got about 15 minutes left to go, 10, 15 minutes left to go on the talk. I could pause and ask questions about that now, but maybe, I don't know if feels like I'm talking into a vacuum here. So shall I just, if Roger doesn't interrupt, I'll just carry on. I'll give him 10 seconds.
Let's see, does anyone have any questions for Dr. Cooper at this point? There's one question, please more about the algorithm to exclude the fat. I'll actually be talking about that at the end of the day today. So we'll come back to that. I'm very excited to talk about it now after all of these comments too. So I think we can address some of those issues in more detail.
Yeah, no, I didn't want to steal your thunder, Roger. So I thought, and I've got other slides about the fat. I can, but I didn't want to steal your thunder, and that's why I did say you do it. And it's interesting to see how successful you are at doing it. But it's great, and that's why I'm sure that's why you use 4 wavelengths rather than 2 wavelengths. And I want to see how you're doing it. So that's great. There are, so I think that's...
Oh, okay, here's another one. What is your experience on sensitivity to small changes in location of the sensor?
In terms of where you put it on, well, depends on the muscle group, of course. If you've got a big muscle group, less of an issue than if you're getting a small one. So if we're doing a continued study, we make a measurement. We always measure from the same distance. We create, you'll see in the papers about exactly where we make the measurement. So, and if it's a measurement in a reasonable time frame, we make an indelible marker on where we put the device. So we put it back on exactly the same place. So it will certainly make a difference if you're off by a centimeter. I mean, I think because you're measuring a different part of the tissue. Now, of course, it'd be nice to be able to image. So if you had multiple sources and multiple detectors, and you can do that, and that's a whole new field. And then that basically, most of brain near-infrared spectroscopy is all about that now. You get multiple sources, multiple detectors, and you image get a topographic image of where the light's gone. And you could do that in muscle, and then of course it wouldn't matter exactly where you put it because you'd get the map. Because that's more expensive and more fiddly, it's rarely done in muscle. But that of course will be the ultimate goal will be to have multiple sources, multiple detectors. The reason why it's really taken off in the brain is because that technique is akin to functional MRI. So the optical technique has a match in an MRI technique which measures brain function. So it's massively mushroomed. Those topographic measurements, and people see people wearing headsets with multiple sources, multiple detectors. It'd be great to get that in muscle, but once you haven't got that in muscle, you do need to put it as close as you can. I don't know that I've done a very detailed scientific study about the differences between different sources and detectors, where you put it. There might be one in the literature which I can maybe try and see if I can find. It's one of those important but boring pieces of work for an academic to do. Unless a reviewer tells you to do it, you don't always do it. So,
That's right.
but there's certainly, we do our best to measure. We make a measurement and we mark the surface if we can.
Okay, one other question here. Can I put something, can I put the sensor in a plastic bag, something that is like an isolation bag? So have you done that where you've put the sensors in plastic bags?
So yeah, so we've got, I mean, it depends on the device, right? So we haven't done we spent quite a while waterproofing the Portamon and picking out what bag to put on it. We by and large, we don't usually, when we're using the Portamon or the Moxie, put a bag on it. But obviously the Moxie, I think it's waterproof, isn't it, Roger, the Moxie?
Yeah, you can use them underwater, yes.
Right? Yeah. So you can't use the Portamon underwater. So we had to put it in an effective plastic bag. And that was quite a lot of work to be sure that wasn't affecting the measurement, because the danger is if you can get light piping. So it bounces around in and out of the surface. So sometimes putting a surface on is worse than not putting it on. I mean, there are issues if you get sweat. I'm concerned about if you've got sweat between a device. That's always an issue I've had, the light could move around and bounce in and out of the tissue. Because remember, the light's going in the tissue, coming out, and what you don't want to do is go in, come out, and pipe along the surface of the tissue. You want it to go deep and come out. So I'm wary of covering it, but if I did, I would do a calibration to make sure there was no difference in the number. And the paper I published in Journal of Biomedical Optics about waterproofing the Portamon, although you don't need to do it if your device is waterproof already, but we went through a number of calibrations as to why to check that was okay. And some coverings were good and some were bad. And we had to check that out and work that out. So that paper's quite good. It was a PhD student, so he spent his whole first year of his PhD doing all that, mostly to check it worked, not to get the device. So that's certainly doable, but be careful. I would certainly do a study with or without the covering, as controlled a study as you can, to make sure it's not having an effect. I mean, if I can ask, why are you actually? Do we know what? Perhaps at a later time you can ask me in the forum why you want to do a covering at all. And I can maybe discuss it there.
Okay. Can the correction for fat layer be done without knowing the scattering coefficient, like in the Portamon where it's fixed?
So in the Portamon, the correction I did with that, you just have to guess. I mean, you have to start off with assumed scattering coefficient. So that one, I just assumed the scattering coefficient, I think. And it's a 2-layer model, and then it. Yeah, so I did, there are measurements of scattering coefficients in muscle, and I used an assumed scattering coefficient. That for my own, which I've not published, so be wary of that. I haven't published that stuff. So I didn't allow, it's not a Monte Carlo model as Roger will say. So it was it was a 2-layer model, the one I did, and I think that's true of the Japanese one as well. But it assumes a scattering coefficient. Now, what I didn't show was the German researcher, Matthias Kohl, who did a great paper where he measured the fat layer and then used that as part of his correction. Because if you measure light at 980 nanometers, you get a direct measurement from the fat. So you can actually use the same device to measure the fat itself for that individual at that site and then correct that way. And I think it's more complicated, so it's a more difficult device to use, but that would be my way forward. I mean, he showed that was the same as measuring the fat with ultrasound or measuring it with MRI. You can measure it optically, and within the same device, you've got a really good measurement. But that's, that beyond a simple device that you're going to measure in for £300-400, at least, in the short term. But I think that's doable. But I was assuming a scattering number.
Okay.
And actually, it's not perfect yet. Yeah.
Okay, so I think there's still some questions coming in. So if you have more questions for Dr. Cooper, please type them into the questions panel here in the GoToWebinar software. And if we don't get to all your questions, then we can follow up in the Discord chat. But I think you've got a little bit more of your presentation left, so we'll let you finish that up, and then we'll take more questions at the end. I'm so glad you spoke at that point, because I was for like 20 minutes just talking into thin air. I had no idea that anyone was hearing me, so that was great. I'm glad I stopped there. Okay, so practical use of muscle near-infrared spectroscopy. So I'll give you some real
exciting data now, or more exciting than the previous stuff. This is a really useful review that Tom Barstow wrote about understanding the technique and its application. So, and it goes through all the stuff I've talked about in more detail and talks about useful terminology. So I really recommend you take a look at this review if you can. It's irritatingly not open access, but I've got a copy, and I'm sure Thomas will give you a copy if you ask him. So that's a really important, I think it's a quite important and useful paper. So we all know muscle activation deoxygenates tissue. So I'm going to start off by looking at the extent of desaturation. There's one measurement. I'm sure it's one you all do. So here's someone, I won't show the video, but he cycles with all-out effort. And as you know, if you do that, the saturation will drop. I'm not sure you've all seen that. Some work I did with GB women's hockey I'm going to describe now sort of illustrates the approach we've been taking with elite athletes. If you use the portal one, but I would think the Moxie would show the same effect. We're mostly talking about saturation number changes. I imagine it'd be the same because they correlate, as I said. We were asked to trial the success of a new training program, but they didn't want the training program to injure their athletes. They wanted to only do the training program on a bike. And we therefore would test the efficacy of the training program, but also not just by standard techniques, but also by looking at near-infrared spectroscopy to see, did it affect their muscle oxygenation? And they were keen because they were concerned that near the end of the games, they were running out of effort. They wanted to do a more training program, be more aerobically fit. The basic technique we did is repeated Wingate tests. So that's 30, 45 seconds, flat out, as high a weight as you can manage, and then pause and then wait, a minute or 2, 3 minutes, repeat it, repeat. And we did 5 repeats with hockey players to measure the extent of the drop in saturation and then the recovery. And this kind of technique is really, it's useful, but it's almost forced on us by this is what athletes are useful to do, what the coaches are happy to do. And you're quite sometimes when you work with elite athletes, you have to do what they want. And they said, that's fine. That's the technique they want to do anyway. So in fact, was part of their training program. So we just put the device on during their training program. So it happened to work really well for our research tools, but you sometimes have to play, bear in mind that. And they're great, as all of you know, working with the athletes, they, especially with their coaches with them, they work really hard and they work till they threw up and were brilliant. So an amazing set of athletes to work with. And what we showed was that post-training, there was a significant increase in the extent of desaturation, a drop in tissue oxygen saturation, however you want to name it. And you can see this here where the grey are the post-training numbers and the black are the flat-out cyclings pre-training. And in the group mean data, it all shows a significant drop in saturation. And we interpreted this as a training-induced increase in muscle oxygen consumption. And we did that because there was no change in training in the HB total. And it goes back to the idea that I really think it's helpful not just to measure a single number, but to use all the tools you've got with near-infrared spectroscopy. So I know the Moxie gives an HBT number as well as an SMN2 number. Some of you may not be using that, but at least you should be noting it in my view, because it can really help interpretation of data. In this case, using the equivalent on the Porter model, in effect, we saw there was no change in that, and we felt this was probably good evidence that what we're seeing was an increase in muscle oxygen consumption. But crucially, and again, something when I'm reviewing papers now, I ask people to submit all the raw data. And what we saw with all the raw data was that each individual post-training saw a bigger increase in saturation. So it wasn't just the group mean data. There's a lot of sports science papers, physiology papers, just measure the mean data. What we showed was that each individual showed this change. And to my naive mind, that's important. You're going to tell a coach, that we're giving you a device, measure that device and use it on yourself. Well, you want to know that each individual gets the same effect with that device. And that can be masked if all you do is show the group data. And especially if you've got a big group of people, where, you can easily get 10% of individuals not showing any effect at all, but the group will still show a significant change. So that's really important. And with this data, but not all our data, I should say, but with this data, they all showed the same change. As I said, really important, and they really liked that, and it was an exciting result for us to get. Now, they then went on, and post-training, things went very well, and Team GB Hockey got the gold medal. at the Rio Olympics, and I can confidently say that 100% of that success was due to the work that we did. No, as if you see my face, you could see I'm joking. Some subfraction of a percent that led to that gold medal we were involved in. But it was great that, in fact, everyone we tested was in the final team, which was really good to know. So a success story for them and a tiny success story for us. And now I want to talk about the quantitative physiology measurements you can make with near-infrared spectroscopy. And there are two specific measurements that you can make and that have been validated. One is a measurement of muscle blood flow, and the other is a measure of muscle oxygen consumption. They both require interventions. So the muscle blood flow requires a rapid venous occlusion, where you pump up a blood pressure cuff to block blood entering the tissue. So blood can't leave the tissue, but it can still enter. And this shows you a sort of model of what that means. If you do a venous occlusion, you see an increase in hemoglobin because the blood is flowing in and not flowing out. So an increase in total hemoglobin, and that rate of inflow is a blood flow measurement. Now, there may not be a saturation change here. So if you were measuring in saturation, you wouldn't see that change. If you're more extreme and do a rapid arterial occlusion, you can measure muscle oxygen consumption. And that's because there's no blood flowing in, no blood flowing out. There should be no change in total hemoglobin. Oxygen will go down, deoxy will go up, and that will give you that rate of those changes, which should be the same, is the rate of oxygen consumption by that tissue, and that's been validated. These are all obviously just made up slides, one PowerPoint by me. There is real data, and this shows the real data from slides, and I'll just move to from that data showing. So the left-hand side is the venous occlusion, the right-hand side is the oxygen consumption. And you can see with the oxygen consumption, which is slide B, the total hemoglobin is not always completely constant. There's some change in it, but it's more or less constant. So what about the MOXIE? Well, there should be no problem using these tools with the MOXIE, as long as you get a rapid cuff infusion, which does require a specific device. You can't just do it by hand. So MOXIE's got a THB, that should work to give you the total hemoglobin measure. So the rate of change of THB, I discussed this with Roger, hopefully that will give you a blood flow measure. I don't know if anyone's tried that, but I'd be interested to see if anyone's tried that. The oxygen consumption measurement with the MOXIE, that should be no problem. This shows you, I think this is they're using a Portamon type device. But what you can see there, the saturation number, which is the one I showed for MOXIE, SMO2, that'll drop. And how fast that drops, that should be linear. How fast that drops will be a measure of oxygen consumption, which you can compare between studies, certainly with it for that individual, and maybe even potentially between groups of individuals. The final thing I want to talk about is oxidative capacity. And for that, we're now measuring rates, not how much something has dropped, but actually how fast it's recovered. So we're measuring recovery rates or slopes or half times. And this shows you here, when you finish exercise, so time zero here is finishing exercise, you see an increase, a recovery of oxygenation in tissue. And if you really want to do it hard, you can actually at each point during the recovery do an arterial occlusion if you've got very accommodating athletes and get an oxygen consumption recovery, how that changes with time. That's harder to do. And if you've got even more money, you can compare those numbers with phosphocreatine recovery, which is measured in an NMR magnet, and which is the high energy phosphates in the muscle, the phosphagen store. And all those rates tend to be mirrored. The recovery rate of oxygen saturation recovery should mirror the PCR recovery and be a measurement of oxidative capacity in that muscle. And also correlates if you've got another NMR machine. No, actually, if you take muscle biopsy, that can also correlate with the amount of mitochondria in the tissue. So it's correlated one measure with another measure with another measure. That comes with caveats, but it's an interesting thing. So don't turn the machine off when you finish an exercise and ignore it. That recovery rate can be really useful. So bear that in mind, as useful as how much you've saturated in the first place. So how we currently analyze our training data, I'm finishing up on this, more or less, is we do these repeated cycles. We measure the extent of desaturation, measure the rate, and then the recovery half time. So what about new ideas? Where am I going in the future? Hopefully, well, one thing is that all those quantitative physiology measurements, the blood flow and the oxygen consumption measurements, they require occlusions, and it's quite difficult to do exercise during occlusion unless it's a particular exercise that actually has an occlusion built in, like some of the resistance training protocols do. So it's a problem to occlude a cleft when you're doing it, when you're cycling on a bike, for example. So what we did about 10 years ago was we took advantage. If you look at a device when you're cycling, you should see with each revolution you'll see an oxygenation change and a total hemoglobin change. And we were able to use that data to interpret how much oxygen was being consumed by the tissue. It was a really interesting paper, but actually, in the end, we couldn't get it to work for individuals. So on the group data, we lumped all the data together and we could get a reasonable sensible oxygen consumption measurement. We couldn't get it to work for an individual. So I think it was a good idea, but in the end, it didn't work. So what I'm hoping to do is to develop a systems modeling approach to aid near-infrared data interpretation, which I've done in the brain. I've got a model of brain circulation, and we've used that model of brain circulation to take inputs like arterial pressure and oxyhemoglobin, intracranial pressure, all those parameters into a complicated model, and out of that comes a predicted CMRO2. So we've published a number of papers in Brain where we take quite complex biological systems models, input near-infrared data and potentially other data we might have, and put it into the model and output numbers that we can't easily measure in real time that we want to measure, like CMRO2, or that's brain oxygen consumption, but in principle, muscle oxygen consumption. That's very much a work in progress to get that to work on muscle data. And I'm waiting to see if I get a grant to do that in the next few weeks. I should know that I've got that grant and start to develop that work further. So finally, I want to remember the plea for your help. This is what I would have done in a bar at Prague. I've been to Prague, so unlike some of you, I guess I've got the benefit of at least knowing where this meeting would be, how much fun it would have been there. As Roger says, it'd be really good to get face-to-face interaction. But if I had more face-to-face interaction, I'd have asked questions about your training, how it compared to mine. So I'm going to end with that, because if you can answer this in the Discord later on, I'd be pleased. So we've done three proper training programs, I guess, recently, last few years. One was sprinters swimming, and another was done with repeated Wingate tests, but both with elite rugby players and with elite hockey players. And all these protocols, they all desaturate. If you do them, you desaturate the muscle, and you also get a constriction. So you get, because they're very high intensity, they tend to constrict the muscle. You get a drop in blood volume, probably a drop in blood flow at the time. See this slide here. So I put it in Moxie terms, even though it wasn't a Moxie device, but so you can understand what it should look like in the Moxie is that during the test itself, SMO2 would drop. Here's the hockey data, minus 109, the swimming data and the rugby data. And THB, what would be the Moxie, would also drop. But then we did post minus pre-training change, and I showed a bit of this with the hockey players. So if we just took the same test post and pre-training, we saw a difference in the saturations. There was bigger saturation change, but there was no change in the volume change. And we interpret that as being this oxygen consumption change, but we don't know. And we're really interested to see if other people's studies show similar things with the Moxie. And what's the time? We've only done this before and after. So when does this change actually occur during training would be really interesting. When do you know when you've done enough training? I don't have that data. Training studies are hard to do, so I'm looking forward to getting that. So any training data you've got, please, if you're happy to share with me, it would be really interesting to share this kind of data and see if we have similarities and indeed differences. So I hope I wasn't too quick. As I say, this talk will be on video, but also I'll be available to answer questions on Discord. But also, even afterwards, my email address was on the first slide. By all means, email me later. I'm more than happy to engage with you and learn from you, as hopefully I can share a little bit of what I've learned with you. This is just to acknowledge there's lots of researchers who have worked with me, but in the particular studies I showed, Ben Jones and Chris McManus, who are my PhD students, who are now both lecturers in sports science at the University of Essex. Of course, all the athletes, all the swimmers, all the coaches and the athletes, and my funding agents here on the right-hand side. And thank you very much.
Thank you, Dr. Cooper. Excellent presentation. Thank you for sharing all that information. We have we'll take a few questions. We have a few minutes left before our next presentation.
Okay.
So we've got a few questions online here.
Okay.
What is THB more sensitive to? Changes in hemoglobin mass or hematocrit of the microcirculation? For example, what might THB look like if plasma volume is increased independent of hemoglobin concentration?
Wow. That's a question Sue Ward asked me ages ago, 20 years ago. I'm not sure I have the answer to that. It's a brilliant question. So I think you need to do the experiment to say it's what it's more sensitive to. So in principle, it's the other thing. What is it? So it's the light that's being absorbed, a change in the amount of hemoglobin absorbing the light in the measurement that you're making. So if you magically just increase hematocrit and nothing else changed, including blood flow, you would see an increase in THB. Plasma volume shouldn't matter if there's still the same amount of hemoglobin in the tissue. So that I need to think about, if you're thinking about a strange thing, because there's a tissue about hemoglobin, then it's arterial and venous and capillary. It's even more complicated than that, actually, because the big veins you can't see with near-infrared spectroscopy. So the big veins are essentially black holes. So any big vein in the system does not contribute to the signal, because once the light goes in, it never comes out. So this is a roundabout way of saying I don't think I can answer that question. So in a short term, but I'm happy to have a go at it later on. But it's a really important question about which one is it. The simple thing I would say is, if you can manipulate those things, do it and see, because THB in the MOXIE is probably not the same as THB measured by the techniques I'm talking about. So actually, if Roger let you have the output, he would have both THBs. So for a change measurement, the MOXIE has the THB measurement I've been talking about here, because it's just easily derived from the 4 wavelengths he's got, as well as his THB derived from his Monte Carlo. And they won't be the same, right? Because I can tell you, we've done many experiments where you try and do things that should be the same, they're never exactly the same, but they'll probably correlate. So that would be interesting, but it would need you access to different outputs of the MOXIE it doesn't have. So I think really good, very sophisticated question, complicated answer. I'm sorry I don't have a better answer at this time.
That's exactly the answer I would have given there as well.
Well,
very complicated.
Important.
Yeah, absolutely important. Yes. Could hair follicle density or pigment explain part of the differences? Let me see. Where did I lost the question here. Between men and women. So could hair follicle density or pigment explain part of the difference between men and women?
I don't think pigment would be. I think they were all Caucasians, and no, they may not have been all Caucasians. So hair follicle density, I very much doubt, because it's going 4 centimeters. So as long as the contact was okay, hair follicle density should not be an issue. And in muscle measurements tends not to be. I mean, of course, if it's a really critical study, you shave somebody, right? Where hair follicle density is a real issue is in brain measurements. That's a much more complicated measurement. And you get people who publish papers where really they're using the same people again and again, and it's because they're bald. So in the brain measurements, hair is a real problem. Muscle, it's less of a problem. And I'd be surprised if hair follicle density explained that difference. In fact, I would be amazed if it was hair follicle density. And pigmentation wouldn't explain why I was seeing the differences between during the protocol as well. So it might explain a one-off measurement, but the color is not going to change in the course of the experiment. So you shouldn't see in the data I showed from the biathletes, when they were saturating different as well. And that shouldn't be explained by a fixed hair follicle density, I don't think. So I think unlikely. So I would say that's less likely to be an issue. Obviously, contact of the device on and having a problem with hair, and that is an issue. I'm not an expert using the MOXIE with really hairy legs. more arms to do it. But it shouldn't be a difference, and it shouldn't affect the change number anyway. But it might affect the absolute at the beginning, but I doubt it.
Okay. So this goes back more to the first part of the presentation. How do you get millimoles? Do you get specific numbers from measuring oxygenation changes?
Right. So in order to get, well, you get millimoles per liter. It's a concentration term. It's millimoles per liter. You get that if you know the path length. So with more sophisticated spectroscopy, you can measure the path length using a time of flight measurement, and then you know the optical path length, and then you get a constant. It's just absorbance, the Beer-Lambert law, then, which has a path length and an absorbance and an extension coefficient. So you get it by the Beer-Lambert law, and the modified Beer-Lambert law, you need to allow for the path length. Now, if you measure the path length, that's great. You can assume a path length, and some studies assume approximate path length. So for the muscle, it's roughly 4 times the source to separation. So you assume, therefore, on the MOXIE, it's probably, well, it's complicated because you've got model 2.5 and 1, so I won't say the MOXIE as an example. But let's say the Portamon 4 centimeters should be a 16 centimeter path length. If you don't want to worry about the path length, you could use units called micromolar dot centimeter. And then it's micromolar concentration change multiplied by the path length. And that allows you to compare between people in units that include the path length when you don't know what the path length exactly is. And of course, the path length, we know the path length varies between individuals. So again, that is an issue. So the units come out. So I guess the pure units on a simple Portamon device, or the MOXIE if you're using the 2.5 only, would be micromolar dot centimeter. But to get micromolar, you need to know the path length, either measure it or assume it. And the assumption won't be out by a factor of more 10 or 20%. But it can differ between individuals. So you difference in comparing individuals. It'll all come out in the biological variability anyway. But yeah, that's probably a
okay.
The numbers come out, yeah.
Okay, we've got time for one more question here, and then we'll move on. So is the repeated acute bouts, how different is the first bout from the subsequent ones, and is that difference meaningful?
Yeah, it is meaningful. I did get Ben and Chris to look at that in a lot. It didn't leap out as being really easy to analyze, but clearly it's important. It's the same way as you look at fatigue in a wingate. So you get a fatigue. The first bout, actually the first one is sometimes a bit of an artifact, but the second one, because you get some sort of priming effect. But the second one is clearly different than the sixth one. The sixth one does not go it doesn't recover as quickly, doesn't come down as far. And we have used measuring recovery parameters, so it should be useful. We haven't done it. It didn't leap out as being a significant difference pre and post training, but it's really important. And you know, there's lots of just looking at power changes. The power is clearly different, of course. So we measure the power. That's different in first and last, clearly, and between during the as well. That's really up to you guys. You know, that's an obvious thing that everyone could do and analyze it. And I would say do that for sure. It's and it's clearly different, and it should be important. It wasn't giving us the easiest way of interpreting our data. Changing training wasn't that. Doesn't mean it wasn't in the data somehow if we'd done it, spend more time on it.
Okay, I guess I'll add to a lot of our hockey trainers have looked at precisely at that. They look at they have people skating all out on the ice, and then they look at how far they desaturate and how long it takes them to recover. They look specifically at that, so they see how people fatigue. So that definitely some people have done that in meaningful ways.
So you're using hockey in the US way. You mean ice hockey, yeah?
Ice hockey, yes. In the Minnesota terminology, yes. Not the thing with the ball.
Not the third most popular sport in the world is hockey, and it's not ice hockey. India and Pakistan, lots of people there.
Oh, sure. Okay. Well, thank you so much. We really appreciate your presentation. Thank you for putting the effort into that.
Thank you for letting me talk.
And sharing that. So we're going to move on straight away to our next presenter.